When developers start using chatbots to train their own AI models, they assume this automates progress with less effort. But a hidden hardware trap is waiting in that workflow. The bottleneck shifts from raw compute power to data quality, creating a scenario where expensive GPU hours are wasted on retraining loops that fail because the underlying generation logic was unstable. Today, we expose how LLM as a teacher workflows force engineers into a trade-off between cheap inference and semantic determinism, often undermining their entire hardware investment in the process. You might be tempted to think that if you have access to a chatbot, you can simply ask it to generate training data for your custom model. This self-training approach sounds like a shortcut around expensive human labeling or massive compute clusters. The logic is appealing. Use inference on consumer-grade GPUs to create datasets quickly and cheaply. However, this workflow introduces a fundamental architectural mismatch that most practitioners overlook until their models start degrading in production. The core issue lies in how modern GPU hardware handles floating-point math when sharing resources among many users or processes. To maximize throughput for high-volume chatbot inference, systems often employ spatial sharing techniques where multiple tasks run on the same physical chip simultaneously. This optimization rearranges the order of mathematical operations to squeeze out performance gains. While this can improve resource utilization by 79% compared to older temporal methods, it destroys semantic determinism. In simple terms, floating-point math is incredibly sensitive to the exact sequence in which numbers are added or multiplied. When a GPU slices kernels and reorders these calculations for speed, tiny variations occur. These aren't just rounding errors, they cause what we call catastrophic token drift. A chatbot might output a specific code snippet today that looks correct but contains subtle logical differences from yesterday's version due to hardware-level variance. If you feed this drifted data back into your training loop as if it were ground truth, the model inherits these instabilities. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This creates a dangerous ROI trap for engineers relying on shared or consumer GPUs. You might save money up front by running inference on cheaper hardware that prioritizes speed over precision. But when that noisy data is used to train a new model, the resulting system often fails to converge correctly. The bottleneck shifts from, "Do we have enough compute?" to, "Is our generation pipeline producing consistent logic?" Research indicates that without deterministic sharing methods which preserve floating-point consistency across runs, multi-tenant environments suffer high drift rates during critical generation phases. The financial consequence is stark. If you generate training data using non-deterministic hardware and then find the model unstable, you must restart the retraining process. This means burning massive amounts of GPU time on cycles that produce no value because the input data was fundamentally flawed. The initial cost savings from cheap inference vanish when multiplied by hours of failed training runs required to fix a broken foundation. You end up paying for compute that produces mathematically inconsistent results, effectively wasting your hardware investment. Furthermore, this problem compounds if you attempt to train on sensitive or encrypted data using standard chatbots without specialized acceleration. Current software implementations of homomorphic encryption are 68 times slower than dedicated hardware accelerators like FPGAs or ASICs when handling large parameter sets. Relying solely on general-purpose GPUs for these tasks creates a massive latency wall, making iterative self-training loops practically impossible at scale. You cannot simply ask a standard chatbot to process encrypted data efficiently. The architecture requires specific hardware optimizations that consumer cards lack. Beyond the math and the chips, there is a critical human variable in this equation: trust versus familiarity. Studies show that users tend to trust AI-generated instructions even when they are logically coherent but fundamentally harmful or incorrect. In an automated training loop where a chatbot generates its own curriculum for itself, the system can converge on incorrect logic patterns without any human intervention to catch them. The more unfamiliar you are with the specific task being generated, such as complex data cleaning scripts, the higher your trust in the AI's output becomes. This creates a feedback loop where low-fidelity training data reinforces model hallucinations rather than correcting them. Instead of improving, the system rapidly degrades, learning from its own mistakes and solidifying those errors into the final weights. Engineers who automate this process without verification layers are essentially building on sand. So how do you navigate this landscape? The engineering bottleneck has moved from fitting models onto hardware to ensuring your data generation pipeline preserves logical consistency across thousands of runs. If you must use chatbots for dataset creation, you need a framework that accounts for floating point variance and token drift. This means implementing verification layers or using deterministic sharing modes where available, even if it sacrifices some raw throughput. For high-stakes applications, the hardware choice must prioritize semantic determinism over raw speed. You may need to accept slower inference times on dedicated instances rather than shared consumer environments. For encrypted workloads, consider that specialized accelerators can offer massive performance gains compared to software-only approaches, potentially changing your cost-benefit analysis entirely. The goal is not to avoid automation, but to ensure the foundation of your training data is as stable and deterministic as the hardware running it. In summary, using chatbots to train models shifts the risk from compute availability to data integrity. A 1% drift in training logic can render months of GPU hours useless during retraining if you are optimizing for speed rather than precision. Understanding semantic determinism is now just as critical as knowing how to write code or select a model architecture. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.